Hello everyone. Today we will continue discussing our topics in synchronous machine. In the last session, we discussed together the power factor control of the synchronous motor, and we agreed that synchronous motor can work in different power factors, depends on the excitation mode, so it can work as overexcited or normal or underexcited motor, and the power factor is going to be controlled according to the excitation magnitude. And we drive together the V curve, and we understood that the V curve can be or the synchronous motor can be used to compensate the power factor if the machine is not loaded, so it can be used completely as a capacitor. So I'm going to add one more thing regarding this point here and continue discussing our topics in motor and solving some problems today. So let's firstly see, guys, starting with the capacitor. You know that for any capacitor, if I have a capacitor like that, and a current I is flowing here, and this is V across the capacitor, I'm expecting that I capacitor equals C dV by dt. So this is the relation between capacitor and capacitor current and volt. So in case of sinusoidal supply, we agree that if you have a voltage V, if this is VC, so the capacitor current is going to be leading this volt by 90 degrees, because dV by dt for a sinusoidal supply is going to make 90-degree phase shift. So this is going to make the current appearing like that. So this is going to be IC, okay? If we draw the phasor diagram of this case, if this is VC, so IC is going to be leading by 90 degrees. So this is the phasor diagram of capacitor. What about our synchronous motor? If the synchronous motor working at no load, and we neglected the machine losses, so this means P input equals P output equals 0. So this is actually an ideal case. It's not practical case because it's impossible to have 0 losses in a machine. But if we assumed or we neglected the machine losses, in this case, we can say that the input power equals 0. If so, and we operate the synchronous machine at overexcited case, increasing the excitation. So in this case, if we go to the equation of the synchronous motor again, so EF equals V terminal minus JIA XS. I mentioned we neglected the losses, which means the armature resistance is neglected because the copper loss is neglected. So in this case, if we draw the phasor diagram of the motor, so this is going to be V terminal reference. IA, in this case, in overexcitation is going to be leading, and you will find that it's leading by 90 degrees, which is typically like the capacitor. So this is the armature current. And in this case, minus JIAXS. So IA in this direction, JIA in that direction. So minus JIA is going to be in the opposite direction. So this here is minus JIAXS. So this means the resultant vector is this vector here. This one represents the excitation loss. What is the power angle here? Right, the power angle is the angle of the excitation volt, which means power angle equals 0. And this is again the ideal case, because if power angle equals 0, this means the active power equals 0. And this is our assumption here. So it's ideal case because the machine is working and we don't have any losses. In this case, guys, we call this mode of operation, or the machine in this case, we call it synchronous condenser. Condenser is a capacitor. So synchronous condenser is nothing but the synchronous motor working at no load and overexcited. So this is the expression of the synchronous condenser. On the opposite side, we can have synchronous inductor. You are right. As you understand from here, synchronous condenser is leading power factor case. So the synchronous inductor is going to be lagging power factor case. But this is on paper. We don't need it in practical life because we're not going to have a synchronous motor working at no load, and we need to absorb reactive power from the grid. This is not practical because all of the time we need reactive power from the grid to supply our machinery in industry. So the synchronous condenser is the practical case that we can have it in our life. Okay. Now, since we understood the concept of the synchronous motor and power factor control, there will be a quick assignment. This quick assignment is due on the coming class on Tuesday. I will make the announcement on eCampus. So here, guys, the assignment says a factory takes 600 kVA. So this is the amount of apparent power that a factory is taking at a lagging power factor of 0.6. So lagging power factor of 0.6, this means there is huge reactive power absorbed by this factory. A synchronous motor is to be installed to raise the power factor to 0.9 lagging. So it has been decided to have a synchronous motor to be installed in order to improve the overall power factor of the factory to 0.9 lagging instead of 0.6 lagging. What is the operating condition of the synchronous motor? He mentioned here when the motor is taking 200 kilowatts. Taking 200 kilowatts, this means it's not no load. So it's delivering reactive power, but it's not no load. Just a moment, guys. Okay. So this is the operating condition again. This motor is gonna work and supply mechanical power to a load. So it's driving a mechanical load of 200 kilowatts, and at the same time, it's delivering reactive power to compensate the grid. So what is needed in this problem? We need to calculate the corresponding apparent power taken by the motor and the power factor at which it operates. So find the apparent power of the motor and find the power factor of the motor. Okay, guys, so this is a quick assignment. So if you have a look to this question here, you will find that you will react with the machine or with the synchronous motor as a regular capacitive load, you will not use any kind of relations for the synchronous machine itself. I mean, you don't need to have or use the relation of the excitation with the terminal volt and the armature current and the synchronous reactance. All of that, you don't need it here. So you will solve this question as if you have a capacitive load, improving the power factor of your system. Okay, why I'm saying capacitive load? Because it's not only capacitor, it's RC load. Why RC? Because it absorbs a certain amount of power. Okay, so the idea again, you have your grid. This is the grid, or let's say instead of that, let's draw like a bus bar. So here is the grid, and you have your load. So this represents the grid or the factory panel. This is the factory load. And the power factor here is 0.6 lagging. And when you install the capacitor, so this is going to be the capacitor branch. It will absorb some active power of 200 kilowatts, but it will deliver some reactive power you don't know. But this reactive power is going to make this one to be improved to 0.9. So the question is, find the power factor of the synchronous motor and the rated KV, sorry, the KVA of the synchronous motor at this operating condition. Okay, so you can assume that it's like electrical circuit question, okay? But just it depends on your understanding of the operation of the synchronous motor as or in the leading power factor mode. Okay, guys, so please make this quick assignment and submit it by the next session. Let's now solve some examples together. So this is an example from our textbook. The example says here 3-phase, 5 kVA, 208, 4 poles, 60 hertz, star connected, which means Y connected, synchronous machine. Has negligible stator winding resistance, so RA is neglected, and the synchronous reactance of 8 ohms. So we have XS equals 8 ohms at a rated terminal volt. The machine is operated as a synchronous motor, so the mode of operation is in motoring mode. From 3-phase 208 60 hertz power supply. The field excitation is adjusted so that the power factor is unity. So we have the first case here is the power factor in normal excitation or unity. When the machine draws 3 kilowatts from the supply. So this is the P input to our synchronous motor from the supply. First question is find the excitation volt. Find the excitation volt. You know, guys, our relation is EF equals V terminal minus J IA XS. Resistance is neglected here in this question. So in order to get the excitation volt, we need to have the current. Terminal volt is given, which is 208 volt. So what is the current? How can we get the current? Look at the operating condition. We have the machine is drawing 3 kilowatts, and you have the unity power factor. So you know the power factor is unity. So from the power equation, guys, you know that power equals V terminal IA power factor. Don't forget to multiply times √3 in case of 3-phase. So this is our relation. And it's a 3-phase machine. So we have to multiply 3-phase times V line, I line. So For the time being, he mentioned that the power is 3 kilowatts. So let's substitute here in this relation. So from here we can say IA equals power 3 phase divide root 3 V line power factor. So we have 3 kilowatts, so 3000 divide root 3 times V line is 208, so 208, and power factor is unity. So from here we can get the current magnitudes. Let me calculate that with you. So 3000 divide root 3 times 208. So the current is 8.33 ampere. Current equal approximately 8.33 ampere. So this is the current magnitude. What is the angle? The angle is 0 because it's unity power factor, and we assume all of the time the voltage, terminal voltage is at angle 0. So the phase shift between current and volt equals 0. Now we can substitute in our relation to get the excitation here. So we can say now EF equals 208 divide root 3 because this is a phase equation at angle 0 minus JIAXS. So XS equals 8 ohms. So I'm going to say JXS, J8 times the current, which is 8.33 at angle 0. So this would give us the phase value of the excitation. So I'm going to use my calculator to do that. So I got the excitation volt equals 137.328. 288 or 2829. Oh, let's write it 288. And the angle is minus 29 degrees. So the angle is a negative sign. Does it make sense or not, guys? So since the machine is working as a synchronous motor, so this makes sense because the power angle in synchronous motor is a negative sign. Nice. So this result makes sense to us. If you would like to calculate the line-to-line magnitude of this volt, so you can multiply the 137.328 times root 3 to get the exact value in line. So this is now the first part, find the excitation volt and the power angle. So the excitation volt is this value, and the power angle is this value. And draw the phasor diagram for this condition. So let's draw the phasor diagram. So simply, we can say now if this is Z terminal, IA is at angle minus 29. So this is IA here like that. So JIA is going to be in this direction, minus J is going to be in the opposite direction. So this is going to be, sorry guys, IA is unity power factor. Let me correct that. So we have here unity power factor case. So the minus 29 is the excitation angle, not the current angle. So IA is in phase. So GIA is in this direction, minus J is going to be to the bottom side. So this is minus J IA XS. So the resultant vector here is going to be our excitation volt. And this is the power angle, which is minus 29 degrees. Okay, so this is part Part B, if the field excitation held constant. Excitation volt held constant means the amount of volt is going to be the same. And then he mentioned, and the shaft load is slowly increased. Shaft load means the power on the synchronous motor, the mechanical power. So the mechanical power will increase, which means the amount of power is going to increase, which means also the delta value is going to increase. What is needed here? Determine the maximum torque or the pull-out torque. You remember, guys, we mentioned that maximum torque or maximum power condition is going to happen at delta equals 90 degrees. But here for a motor, so it's going to be at minus 90. So if you'd like to calculate that, so simply we can say now torque maximum equals P maximum divide omega S. So you know that P maximum is root 3 V line EF divide XS. Sorry, not root 3, it's root 3 V phase. Let me say 3 times V phase E phase divide XS, and delta equals 90 degrees. So this is power. Divide omega S, so I will multiply times omega S here in the denominator. So this means 3 times V phase. So we have already V line. So I'm going to say root 3 times 208 times E phase, which is calculated here, which is 137.28 or 3288 divide our XS, which is 8 ohms, times omega S. So frequency is given, number of poles is given. So you know that omega S equals 4 pi F divide number of poles. So just calculate that. So 4 pi times 60 hertz divide number of poles is 4 as well. So we will end up with 60 pi V omega S. So I'm going to multiply here times 60 pi. So this would give us the maximum torque that the machine will work. I'm going to calculate that quickly here. So root 3 times 208 times 137.3288 divides 8 times 60 times pi. So the torque equals 32.8 Newton meter. So this is the maximum torque that the motor can deliver in this operating condition. Okay, guys. So this is one example, like an application for our synchronous motor. And we could see here how the machine can work at normal excitation. So it's not absorbing any reactive power or not delivering any reactive power. And at the same time, it's driving a certain load. Again, this is not a preferred case in industry because once you have the motor, you should get the benefit of providing reactive power to the grid. So this would help a lot the surrounding loads in order to improve the overall power factor of your factory. So here is the complete solution, guys, of our problem. Okay. Now let's solve another example here. We have here three-phase 5 megavolt ampere, 11 kilovolt, 60 hertz synchronous machine. The synchronous reactance is given 10 ohm, and the stator resistance is neglected. The machine is connected to 11 kilovolt 60 hertz supply and is desired to operate as a synchronous condenser. We mentioned synchronous condenser before, means power equals zero, power output equals zero. Synchronous condenser means we have no load. So this means P out equals zero. So in this question, guys, we're going to solve in two scenarios. The first scenario says if you neglect the rotational loss. So neglecting the machine losses and the armature resistance is also neglected. So this means all the synchronous motor loss equals zero. And you have zero output power, which means this leads to P input equals zero. So this is now the condition in this operation. So for normal excitation, find the stator current and draw the phasor diagram. In case of normal excitation, guys, normal excitation means power factor equals unity. The question is, if the power factor equals unity and the power equals zero, so you know that power equals root 3 V line I line, which is the armature current here, times power factor. We mentioned that this power equals zero. And power factor is unity. So the line volt is impossible to be zero. It's already given here, 11 kilovolt. So this means the only variable that can be zero in this case is the line current. So if the machine is normal excitation in case of synchronous condenser and we neglected all losses, this means the armature current equals zero. So this is like an ideal case, guys. It's not a practical case again because we neglected all losses. And again, guys, ideal, it doesn't mean something we are needing. Sometimes ideal can be something that it's impossible to be implemented in our life. So this is the ideal. So the armature current theoretically here is zero. Why again? Because we have zero power. So power factor is unity, so the current has to be zero. And if you draw the phasor diagram in this case, EF and V terminal will be the same. So if we see the solution here, this is our solution, and this is our phasor diagram, as you can see here. There is no electrical current. Well, the excitation volt is the same as the terminal volt, which is 11 kilovolt divided root 3 in order to be in phase. So this is 6.35 kilovolt. So this is part A. Part B, the excitation is increased to 150% of the normal excitation. Normal excitation means the unity power factor case, which is the operating condition case number A, case in part A. So the new value can be obtained by just multiplying the value in part A times 1.5. This is the new value of the excitation. What do we need here? Find the stator current. We need to calculate the stator current and the power factor, and then draw the phasor diagram. So simply, guys, now we can say, because we are still in delta equals zero condition, there is no load, no losses. So we can say now E is at angle zero. So we can say I equals V minus E divided JXS. V is given, 11 kilovolts, so the phase value is 6351, minus the new value of the excitation is 1.5 times the old value, divide the value of JXS. So this would be the amount of current in this case, and as you can see, it's leading by 90 degrees because this case is over excitation and no losses, which means delta equals 0. So in this case, it's considered as synchronous condenser. So this is a synchronous condenser. And this is the phasor diagram we just drew a few slides ago of the synchronous condenser. This is part B. Part C, if the excitation is decreased to 50% compared to the normal excitation. So this is now 50% of part A. So the new value is 0.5 times the value in part A. Find the stator current and power factor and draw the phasor diagram also. So we are going to repeat the same, but in case of decreasing the excitation by 50%. So similarly, we just, in case of, instead of making this minus 1.5, it's going to be minus 0.5 only. And repeat the solution again. So this would give us this result here. So this is the value of the current. It's going to be the same magnitude of current, but the angle is at minus 90 degrees, which means it's lagging by 90 degrees, and this is called synchronous inductor. And in this case, the power factor is 0 because it's 90 degrees. The power factor angle is 90 degrees. Okay. And the phasor diagram again is going to be the opposite to the synchronous condenser, which is this case now. Okay, so this is like straightforward example for the operation of the synchronous machine at no load, neglecting losses, and one time in over excitation, normal excitation, and one time in under excitation. In part 2, if the rotational losses are 80 kilowatts, so we have some losses now. Losses exist. We don't have ideal case anymore. Find the stator current and excitation volt for normal excitation. So for normal excitation means, again, the current is in phase, power factor equals unity, and we need to get the stator current and draw the phasor diagram. So in this case, guys, since the power factor equals unity, so we can say now 3 V phase I phase cosine theta equals 80 kilowatt. So we have the terminal volt, we have the power factor, so we can get the value of IA. So the current here is going to be 4.2 ampere. It's very small current, as you can see. For that, guys, we neglect the losses. So this is 5 megavolt ampere, and the losses are 80 kilowatt. So we neglect the losses because of that. So can you see if it is working as synchronous condenser, the current was 317 ampere, 317 ampere. And if it is unity power factor, it's just 4 ampere. Okay, so it can be neglected for sure compared to the 317 ampere. Now, if you would like to calculate the excitation volt, so use the same relation again. So Vt minus Jx V terminal is here. This is the phase value minus the current at angle 0 because it's unity power factor times 10 at angle 90 Jxs. And you would get the excitation volt. If you draw the phasor diagram, so this is Vt at angle 0, and this is going to be EF, and it has to be in negative angle delta like that. Okay, please guys take care that this example is solved, or this part of the example is solved incorrectly in the reference, in the textbook. I don't know why by mistake they get the result here as like as generator, not a motor, and they provide the angle, power angle delta in positive sign, and they draw the phasor diagram for a generator, not for a motor. So this is incorrect. So the right representation is what you can see here. Okay. So this is, guys, about the synchronous motor operation in case of different power factor conditions. Now, guys, I'd like to just refresh your knowledge in one important point, which is in case of connecting a synchronous generator to grid through a transmission line. Regularly, guys, when we connect a generator to grid, we would have firstly a transformer, then transmission line, and so on. Sometimes we use like double lines like that or many lines. Why? Just to have a continuity if this line is disconnected, so you will have other lines to transfer the power. So this is more reliable for any grid. What is the condition of power transfer? So the power transfer, guys, or the generated power now can be considered as if we add the synchronous reactance of the transmission line to the reactance of the transmission line to the synchronous reactance of the generator. So I can say that the maximum power that I can have at the receiving end here is going to be the excitation volt of the synchronous machine times the VR, which is the receiving end of the transmission line, divide X total. X total is the synchronous machine reactance plus the reactance of the transmission line divide number of transmission lines because they are connected in parallel, as you can see. So in this case, guys, we can consider as if the complete transmission line system as a part of the generator now. So we can consider that as VR is the terminal volt of our machine, and this reactance is added to our synchronous generator. And this is going to be now the maximum power that we can deliver at the receiving end here. So in this case, guys, the power received here is going to be a function of the transmission line reactances in our circuit. For that, guys, in transmission systems, the transmission reactance is very important. We use what's called STATCOM. So STATCOM is static compensator. So these compensators, guys, are used sometimes to improve the reactance of the transmission line. What is the purpose? If we improve the transmission line reactance, this would increase the amount of power transfer. Okay, guys? So how can we do that? So STATCOM or compensator, static compensator, is nothing but a power electronic device connected to a stored energy element, regularly capacitors, and it injects the reactive power to the grid in order to improve the operation of the grid, like adding or changing or controlling the transmission reactance. So this would help a lot in improving the performance of the power transfer on our grids. Okay, again, the topic, if you would like to search for that topic, it's called STATCOM or a static compensator. Okay, nice. Okay, let's solve another numerical question here. So we have here three-phase 250 horsepower. So this is the output power. 2 or 2300 volt, 60 hertz, Y connected, non-salient, which means cylindrical, rotor synchronous motor, has a synchronous reactance of 11 ohm per phase, and doesn't mention the armature resistance here. The question says when it draws 165.8 kilowatt, so the machine draws, so it's working as a motor and drawing some active power. When the machine draws this amount of power and with a power angle of 15 degrees, so this is delta, neglect the ohmic loss and find the following. Firstly, determine the excitation volt per phase. So we need to get the value of excitation volt. And the power angle is given here. The synchronous reactance is given. So you know that, I think this is not solve a problem, so we're gonna solve this together here. So you know that power equals 3 EF VT divide XS sine delta. So we have the power, we have the terminal volt, we have XS, we have delta, so we can calculate EF. Okay, so let's do that here. So we can say EF equals, if you'd like to get it in line, so I'm gonna say I will remove this 3 from the equation. So it's gonna be EF line and V line in this case. So we can say EF equals P times XS divide V terminal sine delta. So we have 165.8 times 10 to power 3 times XS, which is 11 ohms, divide V terminal line, which is 2300 times sine 15 degrees. So this would give us the excitation volt. Let's calculate this here together. So 165.8 times 1000 times 11 divide 2300 times sine 15 degrees. So the excitation volt is 3063.75 volt. So this is the excitation volt line to line. Then it's required to determine the supply current. So we can say the supply current IA equals, since this is a motor, so it's going to be V terminal minus EF divide JXS. So V terminal is 2300 divide root 3 at angle 0 minus the excitation volt, which is 3063.75 divide root 3 at angle 0. sorry, at angle 15, divide the value of JXS, which is J11, and you can get the current here. So I will leave the last part, guys, of the calculations to you. Okay, so it's very simple to do that. So this is the armature current, and you will give also the power factor. Part B, sorry, part C. So this is A, this is B. And C, term of the supply power factor. Actually, you got here the current and angle. So the power factor is going to be cosine the phi of the armature current. So you would get here the current with angle, so you can calculate this power factor. If the mechanical load thrown off and all losses become negligible. So if let's guys do the calculations here. Sorry, let's guys make the calculation here because we may need it to solve the other remaining parts here. So I'm going to calculate the current firstly. So 2300 divide root 3 minus 3063.75 at angle. By the way, guys, this is motor. So the angle here has to be minus 15, correct? So this angle here has to be minus 15. Divide J11. So the current is going to be correct that. So the current is going to be 165 at angle 64 degrees. So this is the current, and the power factor here is cosine 64 degrees, which is 0.438 leading power factor. So this is the parts B and C in numbers. Now, if the mechanical loss or mechanical load is thrown off. Mechanical load is thrown off means P out equals 0. So here, this means P out became 0. And all losses are negligible, so you have now input power equals 0. First thing is determine the new line current and supply power factor. So this is very practical, guys. Practical question. So did he mention anything about the excitation? He didn't mention anything about the excitation. Therefore, the excitation, guys, is going to be constant because excitation need to be changed either by an automated system called AVR, or you can control that manually. However, if you throw on the load, it will not change the excitation. You have to have the AVR system in order to do that. So I'm going to consider the same excitation value we have before and start repeating the calculations again based on having the same excitation volt. But in this case, the power angle would be zero because all the load is thrown off. So I'm gonna create a new slide here. So our new case here, the power is zero because delta equals zero. And we have the value of the excitation volt, which is 3063.75, and this is line. So we have EF line 3063.75 volt, and we have the V terminal equals 2300 volt. Now, what we need to calculate is determine the line current and the supply power factor. So I'm going to repeat part B again in this case. So IA equals V terminal minus EF divide J XS. So again, 2300 divide root 3 angle 0 minus the excitation volt, which is 3063.75 at angle. This is now going to be 0 because we have delta equals 0, divide J11. And this would give us the new current. So this gives me here, guys, 157.8 I or J. So this is, let me make it in polar format. So this is at angle 90 degrees. So in this case, the power factor equals cosine 90 degrees, which is 0 power factor. And 0, as you can see, it's 0 leading power factor because the current is leading by 90 degrees. Okay? P or 2 here, draw the phasor diagram of this condition. So if you draw the phasor diagram here, guys, it's going to be the same as the synchronous condenser. So this is V terminal, this is IA leading by 90 degrees, and this is going to be minus JIAXS, and you can say that the complete vector here is going to be the excitation volt. So this is the phasor diagram of this operating condition. Another question here, by what percent should the field currents be changed to minimize the line current of the supply? This is a very good question. By what percent should the field current be changed? Should the field current IF? This is not F, this is IF. to minimize the line current. Minimize the line current, if we go to the V curve, guys, the minimum line current we discussed before is only achieved at unity power factor. So the minimum current means the operation in normal excitation. So it's this question here discusses that, or would refer to that, if you change the power factor to unity, what would be the amount of the excitation in this case? Or what percent should the field current be changed to minimize this current to this minimum value? Actually, in our condition here, we don't have losses. We don't have loads. So as you remember, we just discussed this a few slides ago. In case of normal excitation, so this is here part 3. In case of normal excitation of synchronous condenser, the IA is 0. Because you don't have any losses, you don't have any power. And power factor is unity, so this means IA has to be 0 because the power is 0. So this means you would change the excitation volt until having current equals 0. What is the new excitation volt? So we can, since the excitation is 0, so the new excitation volt, so we can say EF new is going to be the same as V terminal. So you have the other value of the EF here, and the new value is the same as V terminal. So you can say the change in EF equals EF new, which is V terminal, minus EF old divide EF old. I'm just referring to the old value. So I'm gonna say here the excitation is 2300 minus 3063.75 divide 3063.75, and I will multiply this times 100%. So if you do that, guys, 2300 minus 3063.75 divide 3063.75 times 100. So you would find that the reduction is by 24.93%. So this is the reduction in the excitation volt in order to achieve unity power factor or minimum armature current. Okay, guys. So I'm gonna stop here at this point. So for the time being, guys, we solve sufficient problems on the synchronous machine, on the synchronous motor, synchronous generator, and we discussed all of our topics in this synchronous machine. I will post the homework on eCampus, okay? And in the next session, we will start in a new topic, which is the induction motor. Thank you so much, guys, and see you in the next class.